active moment in the life of this set of ideas, and I hope it's a very successful meeting. So let me just give some words about the IFT. Most of you already know it, but for those of you who may be new to it. So we are a joint institute of Universidad Autónoma de Madrid, which is the campus we are located on, and the CSIC, the Spanish Research Council. And we have a very active profile, so we have many conferences like this one, seminars, and we have a visitor program. So besides these kind of conferences, like today's these days, if you're interested to come and visit, please let us know. It could be for a few days, just to give a seminar. It could be for more extended visits, up to several months. So please just enjoy the meeting, and I hope that you enjoy the IFT now and also in the future. Thank you. So let's start.
Okay, so our first speaker is Cumrun Vafa, who is going to talk us about new perspectives in string cosmology.
Yes. Thank you. So first of all, I would like to thank the organizers for inviting me and organizing this conference, which was, I think, quite amazingly timed. I don't know how they managed to get the timing so perfectly. I could not have anticipated for sure. So I'm going to talk about some aspects of connections between string theory and cosmology. So it's part of a talk, it's related more or less very close to the talk I already gave in strings. So for those of you who have seen it in strings, I apologize. There's going to be a few more points that I emphasize, which is different from what I talked about in strings, and some extensions that I will mention. So it's based on the two papers that came out in the summer, one with Obeid, Oguri, Spodineko, and the other one with Agrawal and Obeid and Steinhardt. And there's also another paper coming out hopefully soon that with Hiroshi, with Palti, Oguri, and Shu, and I think Palti Eran will be talking about it today, this afternoon, I think, right? Or today? Yeah. Okay, so the plan for my talk is going to be, again, reviewing why we originally think that de Sitter must exist, and then talk about the caveats in it, and then formulate a new Swampland conjecture, which puts a lower bound on the gradient of the potential of the scalar fields of this form, gradient of scalar field being bigger than C times V. Give some further evidence based on Swampland distance conjecture and the stir entropy, and this is going to be, this part of it I'm going to only talk about very briefly, maybe in one slide. This part of the connection between this conjecture and the Swampland distance conjecture will be covered by Eran. I talk about cosmological implications of two of these Swampland conjectures. One is the de Sitter one, and the other one is the distance one. And then I also mention some potentials for refinements, if there is, and then I will conclude. So again, very briefly, why do we believe, why do we care about de Sitter? Is that because we think we live in one of them. This is the usual picture that we usually draw to say that, well, we have a cosmological constant which is positive, and so having a cosmological constant implies that you have to have some such profile. In string theory, we know there is no free parameter, therefore this must be at the bottom of some hill, some potential, and you can vary it. So this is the usual picture we have for how the cosmological constant is realized in string theory in particular. And then the question is, why do we have to assume that the cosmological constant is constant? In other words, why the dark energy cannot roll? And then there are various arguments that suggest that that should not be rolling. The first one is that if it were to roll, this field will be changing over time, and this field couples to something, and so therefore it should lead to observational consequences which are time dependent. For example, you would think if phi couples somehow to the fine structure constant, it should vary over the course of the evolution of the scalar. Since it has been presumably rolling in the past, we would have had some variation of the things like the fine structure constant, but we have strong bounds on these kind of things. For example, from z equals to 1 to now, delta alpha over alpha is less than 10 to the minus 6. So these are relatively strong bounds. Also, the coupling of the scalar field to matter would give you some new force. Exchange of the scalar field will give you new forces. And this would, if you have some matter that would correspond to the exchange of them, you would imagine not all the matter couples universally to this, so there'll be some violation of the equivalence principle naively. And so there will be viewed as some kind of fifth force which would be measured by some apparent such violations, and there are no, there are strong bounds on the fifth force. So all of these would originally suggest that this idea is not a good idea, and we have to have a constant, cosmological constant rather than a rolling one. These are not good arguments. In particular, in the context of string theory, they're not good arguments, in my view, because it's true that the scalar field should couple to something, but it doesn't have to be our sector necessarily in every aspect that we have measured. So it could be, for example, you could have a sector like the scalar fields are part of a dark sector. In a sense, the fact that the dark matter couples weakly to us is a fact. It's an experimental fact. We know dark matter couples weakly to our sector. It does couple gravitationally, but we don't know if there's any other way other than gravitationally. Up to now, there are strong bounds on the strength of it in terms of its interaction to us. So why not this scalar, this quintessence field scalar, could be a part of the dark sector? It sounds very natural. It unifies the dark sector with the dark matter with the dark energy into one sector. So it wouldn't be that exotic. But there is one more feature of the quintessence model, which is very strange, and that is the value of the potential, the cosmological constant, is of the order of 10 to the minus 120 or something in fundamental units. But not only v is small, but also, if you want to have a quintessence field, the slope is also smaller than or equal to that again. So you would say not only the value is small, but also the slope is small. That sounds like fine-tuning. And therefore, this sounds too bizarre. So original view is that, well, v can be this small, but grad v better be 0. Otherwise, that's ridiculously small. Unless there's some reason where grad v is of order v, in which case it will explain it. By the way, note that this kind of argument, we already made this mistake once in our community. You remember the days the cosmological constant was supposed to be 0? And we were trying to prove it using string theory because it was the most natural number to be 0. Why would it be 10 to the minus 120 or smaller? Okay, so that's not a good argument to say it's small, but especially if there's a relation between grad v and v in some sense related, it doesn't mean that there's a double fine-tuning. It will be the question of why the v is whatever it is. So unlike the ADS, where constructing a supersymmetric example is the bread and butter of string theory and holography, the de Sitter is not so easy to get. And there have been very heroic efforts by many people, in particular the KKLT approach and also the LDS scenario, where there have been attempts to come up with scenarios. And in my opinion, I mean, there's a huge amount of literature on them, and there are many attempts in doing it. And there are pros and cons, and people are still debating whether the construction has succeeded or not. So I don't want to get into assessing this, but given that it's not settled, it's natural to ask what happens if we do not believe these are existing and study the alternatives. Now, in fact, to construct a de Sitter, one needs to do something rather exotic. Namely, classically, we know, for example, one Maldacena Nunez no-go theorem, that in the limit of supergravity, that means when the curvature is small, when the Planck curvatures are not Planckian, then you don't get de Sitter in M theory. Now, one could say, well, that's the way it is, but why? Why should it be like this? Why should we not be able to see it even in the classical limit? Why should we have to appeal to some exotic feature? Is the theory trying to tell us something? Or somebody is being malicious? Right? I mean, it's possible that you have to look harder and more deeper on some other corner, that there's this answer somewhere there. But naive argument is that if some picture is not failing, then there might be a reason. Some people compare this to the saying that, oh, just like hydrogen atom is classically unstable, doesn't exist, but quantum mechanically exists. Therefore, de Sitter is like that. I don't think this is a fair comparison. It's not like saying that hydrogen atom is not quantum mechanical or not. We are talking about quantum mechanical M theory. It is the same as if it's like this. You have a quantum corrected Maxwell's theory coupled to photons, coupled to the electrons. If that does not allow hydrogen atom, but quantum corrections on top of that allow the hydrogen to exist by some miraculous reason, that would be the analogous of this. So it's a bit strange that one is trying to have to go to such corners to try and construct de Sitter. And to me, it's one of those exotic features that to me, is a telltale sign of whether we should really think de Sitter exists or not in a quantum mechanical sense either. So we should dare to therefore ask, what if there are no metastable critical points of V with positive value? For example, could we have a lower bound on grad V bigger than some positive constant? Well, this cannot be like this because we know there are supersymmetric theories which have zero cosmological constant, and in those cases, V can be something, if you deform it, you can have some fields in the theory which are massive, and therefore you will have potentials like this. And if you go phi sufficiently close to 0, for which this potential is trustable, you can see that the grad V can be arbitrarily close to 0 as you approach phi to 0. So there cannot be a bound like this. But you could ask if there could be a bound like grad V is some function of V. For example, could F be a function which is itself related to the potential by some positive constant? So could we have such a relation, in other words, is the next natural question. In fact, let's check it. So this is trivially satisfied for all the ADS examples because V is negative and grad V, even though it's 0 in the ADS case, there's no problem because this positive number is bigger than negative number. It even is true for the case where you have zero cosmological constant because of this equality sign. But how about the case when V is positive? Well, how do we get V equals to positive? Well, let's start with the cases that we actually know exist. Start with a supersymmetric example like Calabi-Yau and deform it. When you deform it, by all the possible deformations, it corresponds to leading order of deformation to some bunch of massive fields of this form. And if you compute grad V over V, you get something of order 1 over phi. So as phi goes to 0, this becomes arbitrarily big. So grad V is bigger than V for phi sufficiently small. And so there's no problem. And in fact, this is bigger than order 1. So you might say, well, we can make this phi to be very large, in which case we can make this as small as we want, except that we don't trust this kind of formula in that limit. And so therefore, there's no contradiction. And therefore, in the regimes where we trust it, it satisfies grad V is bigger than V. So what this says that all supersymmetric theories, if you deform them, satisfy this conjecture already, because any deformation of supersymmetric ones will look like this. So that's already a non-trivial statement that no near supersymmetric ones would violate this conjecture. That's number one. And already there is much harder to find examples if it's to be violated. But actually, one can do better. So consider the supergravity limit of M theory, where we just look at the usual bosonic pieces of the action, some curvature term and some flux term. And if you compactify this on some manifold, you get some effective theory as a function of the moduli, like this metric moduli or flux moduli. So you can create a huge number of examples of V of phi. So then you can say, okay, I have my toy model of this space of all possible phis by picking my manifold. So if you're interested in going to 4 dimensions, you take a 7 manifold, open up a math book, pick your favorite 7 manifold, put it in and see as a function of the metric variations what you get. You don't have to solve any equations because I didn't assume that you're at the critical point. What kind of properties does V have? Is there any generic feature that V has? That was the question that is natural to ask. Is there some aspect of V that is universally true for every such manifold? And in fact, already one feature Madasina and Nunes point out, that feature is that this V has no critical points when V is positive. So for positive V, this does not have any critical points. For negative one, there are. But for positive one, there's just no critical points. That already shows you something. That is, if somebody said, oh, take a generic function, does it have critical points? Sure, why not? Positive, negative, yeah, sure, why not? So genericity arguments are incorrect in some cases. In this case, it's incorrect. The Madasina-Nunes theorem says that you cannot just say something is generically true, therefore it must be possible, because there's a huge number of 7 manifold, and there are exponentially large number. That's not a good argument. The no-go theorem says that actually does not work because there are extra reasons it doesn't work. So what we think is generic, we have to have a prior for what generic is, and that may be a wrong prior. So it's not a random function. Not every function is the ones that appear here. And indeed, there are no critical values for V when V is positive in the context that we get here. In fact, we can sharpen the Madasina-Nunes no-go theorem by the following argument. You can actually say the argument is very simple. You just take the 7 manifold and rescale as a function of the volume. That gives you a direction in the scalar field space. And you can always show that that direction satisfies a gradient of v bigger than v up to some constant, and the constant you can compute. It's this depending on which dimension you go down to. So for example, if you go down to 4 dimensions, you get some constant of the order 1.6. So you say grad v is bigger than 1.6 times v. That's an amazing feature of all these potentials. You could say, well, okay, this might be an exotic feature of the classical version of gravity, but actually, this 1.6 is actually saturated. It's not a random bound. In the ADS 4 times S7 example, near this region, this is saturated. So it's a good bound. It's not only, it's a sharp bound. You cannot do any better than this. That grad v is bigger than v of the order 1.6 is actually realized. So it's a sharp bound. It is there, and so it's meaningful. So therefore, we take this then seriously. You can have a bound. It's realized in examples we understand in the ADS context. And could it be a general feature? In fact, if we assume strong energy condition, you can get similar bounds. If you start with a theory in capital D dimension and then going down to lower dimension D, you get bounds of this form. And if you assume the null energy condition, you get another bounds of this form. So you can get these bounds of different types. For example, the null energy condition bound will give you a bound in 4 dimension of the order of 1.2. Now, both of these are violated in string theory, so I'm not saying these are the bounds you should take seriously as the final value, but it's interesting to show that these bounds give you some numbers of order 1 very naturally, and at the very least, we could say that in compactifications in string theory, where we don't use ingredients which violates, let's say, the null energy condition, you cannot get better than this. That's already a statement, independently of how you do it. So these are kind of more generic statements. And so we learned some interesting facts, I would say. There are other examples. This has nothing to do with supersymmetry. Often people think that the only knowledge we have in string theory is from supersymmetry, even though most of them is true, that's what we have. But there are occasionally a few examples. One example being the heterotic O16 cross O16 string in 10 dimensions. This is a non-supersymmetric chiral theory in 10 dimensions, has no tachyons, perfectly fine in 10 dimensions. And when people studied it back in the late 80s, we were dismayed that the cosmological constant didn't vanish. At that time, it was supposed to vanish, by the way. We were trying to see why the cosmological constant was 0, and we didn't think it's a good feature that's positive. It ended up the value was positive. And in fact, it was rolling type. Namely, when you go to weak coupling, it rolled like this. But again, you can compute grad v over v for that. And for sufficiently weak coupling, we trust this computation because it was done with the one loop. So the leading order will give you 5 over root 2. Interesting. So these are, again, examples of situations where we understand from first principle how to compute it, and we get these kind of bounds, satisfying these kind of relations. In fact, extending an argument by Hertzsprung, Kochruth, Taylor, Tegmark, and also by Razzi and Zagerman, one can fill out a table of what happens if you take various fluxes, turn on the Raman fluxes, and going to various, include various orientable planes and d-branes of that same dimension for a fixed dimension of the brane. Now here we are using ingredients where you could have violated the null energy condition because orientable, you're allowing for negative tension orientable planes. But even for those, you get bounds of this constant of these types. And but some other people even have filled these two. So there seems to be a reasonable statement that if you if you go to the weak coupling regime at least, you can actually prove it by at least, not prove it, but you can see in these examples that it's quite natural to have such a bound. And so the upshot is that the conjecture is not unreasonable, where C is of order 1 in Planck units. Therefore, this also makes quintessence more natural with V prime of order V. Because that was one of the observational bounds says V prime cannot be much bigger than V. And indeed, this is the kind of a natural connection with this. It means that it is as close to being 0 as it can with that V in this context. So it's equivalent. It's a replacement of saying you're at the minimum of the potential. You're at as close to a minimum as possible given the value of V. Now, there is a heuristic link that will be discussed later by Eran, which connects the distance conjecture to the de Sitter conjecture. The distance conjecture as you may recall, is the statement that if you go far enough in scalar field moduli, you get a tower of light states, which grow exponentially with the distance in the scalar field. And this gets related to the de Sitter conjecture in the following way. If you have a tower of light states, the spacing goes down, and therefore you get a huge number of states, exponentially large, because there's a huge number of them left over. And therefore you can estimate the entropy, and you would expect entropy to be related to n or some power of it. And therefore you would expect, since the de Sitter, the Gibbons-Hawking entropy for de Sitter space is related to the potential, you find the potential should go like e to the minus alpha phi, at least when you're at far away points. And this gives you the de Sitter conjecture at weak points. In other words, the fact that the weak coupling version of de Sitter works may be a general thing one can actually establish beyond the examples we have checked. Now, this will be extremely interesting. It will tell you that if the de Sitter conjecture is false, or if it's true, it's going to be hard to establish it, because we will have to describe what happens in the interior at strong coupling points, or at least not at parametrically weak coupling points, in which case the question is whether is it weak enough or not, and then that brings us to the center of controversies, whether we have examples. So that nucleates the question that's not going to be easy to establish it. That is why these efforts to establish it will be heroic in terms of the attempts, because you have to somehow get to these very weak coupling type points. Anyhow, I won't talk more about this because Aaron will talk about it in much more detail. So let me then move on to the cosmological implications of it. So, we take the grad V is bigger than a constant times V, and also the distance conjecture says that you get a tower of states which are light. So for a given effective field theory, if you don't want to have light states, you have a bound on the range of the scalar fields. This is the work we did with Hiroshi a while ago. So we divide the discussion of the implication of these two conjectures to the past, present, and the future in cosmology. So in the early universe, the very early universe, the constant C is related to the slow row parameter. To one of the aspects of the slow row parameter is the half of the grad V squared over V squared. This is related to the epsilon. It's traditionally denoted by epsilon. And the current observational bounds on the B mode lead to, at least for the typical models that's in textbooks for inflations, to epsilon less than 0.004 or C less than 0.09. But these models already are in trouble when you combine it with spectral tilt, so in terms of experimental observation, regardless of C. But if you look at the other models, which are these plateau models, which are more favorite, then you find that C should be less than 0.02. Now, people have talked about other kinds of examples with multi-field inflation and this and that. So this is not a claim that this is the bound on all possible inflationary models, but gives you an idea that for typical models that you take, you will have to worry about whether this number is reasonably small or not. Remember that we got 1.2 using null energy condition and so on. So this cannot be too different from 1. Whether 0.02 is too small or not, I don't know, but it shows that there's some tension with this value being of order 1. Moreover, the number of EFOs being greater than 60 leads, for example, in the plateau models, to the range delta being bigger than 5. Again, this is a little bit on the high side, but it's not going to rule out inflation because order 1, 5 is also order 1, so we don't really know. But it says that there are two worries to have in the context of inflation in these contexts. So that's the past. The present epoch, so by definition, we cannot be, if we believe the de Sitter conjecture, we cannot be in a situation where we have a cosmological constant, so it should be rolling. And you can see what the bound could be on the slope of the potential. And if you look at the bounds for the value of W of the dark energy, which is the pressure over the density for the dark energy as a function of the Z parameter, the redshift parameter, so you find that you get this black. You find that the W is below this black curve. So you can see the value here, the W on the vertical axis, and Z is the redshift axis. So that the value of W should be less than this axis. W equals to -1 would be the case if you had the cosmological constant. And as you can see, that's perfectly consistent with experiments. But it doesn't have to be with the current bounds. And in fact, if you allow C, the slope, V prime over V of order of 0.6 already, you still are perfectly fine in this bound. So you can be with no problem with the current experimental bounds. you can be at c is equal to 0.6, which is certainly an order 1 number, and that makes sense, potentially. And it'll be interesting to see to what extent these can be shrunk down. The current observations are underway, which will potentially put much more interesting limits on what W of z could be, and that will be interesting to see where that leads. Okay. Okay. So if you use this, you find that there is a bound of the form 1 plus W is bigger than 0.15 c squared today. So W today cannot be minus 1. It's actually shifted away from minus 1 by 0.15 times c squared, where c is that order 1 number. So you pick your favorite c. What could be the reasonable number there? I don't know, but it certainly says that we're going to, if this conjecture is true, we're going to be able to see presumably what this W is, because it cannot be exactly minus 1. We can also talk about the future. Well, if we lived in de Sitter space, the lifetime of the universe before it makes a phase transition can be arbitrarily large, because there's this barrier it has to tunnel. And so this could be arbitrarily long-lived. Well, that's interesting. But there is an interesting fact today that the current age of the universe, also related to the inverse of the Hubble parameter, is of the order of 1 over square root of the dark energy. This is a version of what's called the coincidence problem, a version of it. Well, this could be, you could say this is accidental. If we waited longer and longer, this would have presumably been still there, and these numbers would have, lambda would have stayed constant, and so this would have been incorrect. So this would be a property of now. But that is really unsatisfactory, somewhat at least, and it'll be interesting to have to see if there's any explanation of this. And as I will now argue, the de Sitter conjecture actually explains this fact by saying that the lifetime of the universe cannot be more than a few order of the Hubble time. So this would say that the typical time in that universe will be the one we are observing now. There is no accident. So this actually is, to me, an aspect of this conjecture which has not been studied as much since we discussed this, that actually solving aspects of the coincidence problem, which otherwise in the context of the metastable de Sitter is a black box, and why it's true is a mystery. So anyhow, basically you study what happens if we are over here and it's flowing. It could go negative potential, it could go flow like this. If it goes negative potential, then you're going to make a phase transition. Our universe will not be the same, there will be a crunch. If it goes like this one, you cannot go too far, because phi cannot go at most by order 1 in Planck units before light tower states come in. So either way, you're going to estimate how fast, how close it is to getting a new phase of the universe. There should be a phase transition. And using that, you can estimate that the number of e-foldings, the number of Hubble times that we are left to do, is 3 divided by 2 times omega. This is the share of the dark energy of the energy pi, which is 0.7 or so. Delta over c are these two order 1 numbers in these two Swampland conjectures. So we see that the lifetime of the universe before it undergoes a phase transition is of order 1. So these are, again, an interesting aspect of this conjecture. It tells you that we are naturally at an age related to the dark energy. The dark energy and the Hubble time being related is not an accidental statement. And this, to me, is actually one of the most remarkable aspects of this conjecture. But there's actually more. And this is an aspect I haven't talked too much about in the string, so let me emphasize this. So how are we going to discuss about the cosmological constant problem? Well, in the anthropic way of looking at it, you just have a small enough, more and more fine-tuned in such a way that we could have existed and have a structure formation to describe why we can observe the universe today. But that's not going to be available now, because cosmological constant is not constant. It's rolling, it's dark energy. So how could we explain that that's so small now? But actually, that's interesting, because we can have a new perspective on it. You see, suppose V is positive. You can parameterize the potential in this way when V is positive by some indefinite integral like this, with some d phi over m of phi, and m of phi is going to have a mass scale, because phi is the dimension of mass. So you have some d phi over m phi, and depending on what potential you have, you can have m as a function of phi varying. But there's some mass scale associated with various values of phi. Now, suppose you start with V of the order 1 in early universe. That's reasonable, right? Planckian energy. Something of the order of Planckian energy. And now you go down to 10 to the minus 122. In other words, the change in the log of V from the very beginning to now is about minus 280. Well, if you just put that integral, you get an expectation value of average value of 1 over m during this period from the beginning of the universe till now, times the range of this field. I'm just doing this average sense. This should be of the order of 280. In other words, if delta phi, if you take it to be of order 1, you get a mass scale. I'm doing a little bit funny inversion, but roughly you get a mass scale here of order 1 over 280 in Planck units. In other words, you find that the typical mass scale associated to the scalar field is of the order of 10 to the 16 GeV, which is the Gutt scale. So this would suggest basically one version of saying that the cosmological constant today is somehow related to m Planck divided by m phi in this form. And m phi being m Gutt is not that exotic, a factor of 100 or so less than m Planck, will give you these kind of relations. So it's a totally different perspective on the cosmological constant problem that needs to be developed further, and I find this quite promising, actually. So we have talked about observational consequences. 1 plus w today should be different from 0, and the dark sector couplings should be changing over time. So there should be some time dependence in the dark sector, and that would be interesting to explore. People have described some possible refinements of this conjecture. So a number of papers have raised the issue of possible unstable regions in the field space. For example, in the context of the Higgs potential at the origin of the field space, or some other examples. So there are two possibilities. What they find is that is not a contradiction with the conjecture, but what they find is that you get some features which from the effective field theory viewpoint sounds exotic, which of course could be true because effective field theory is precisely what the Swampland conditions is trying to correct. So that's not a good argument that these don't happen, but they seem a bit exotic. So either the Swampland conjecture is true and these cases will give you some interesting, strong statements, or some people have suggested some modifications of them, for example, based on suggesting that the metastable de Sitter is what this conjecture applies to. So in other words, when the Hessian of the V has negative direction, that's not the region where we're talking about the conjecture. It's only for the regions which the Hessian has positive values. So either it's a very strong statement or a refinement, and either case would be interesting to study both versions, in my opinion. So the conclusion is that, since I've run out of time, it seems not unreasonable to believe metastable de Sitter is not realizable in quantum theory of gravity. And this, together with another Swampland criteria, which is this range of it, leads to some tension with inflation. And present epoch must be based on quintessence. And the universe is about to undergo a phase transition on order 1 in Hubble time. This is also my last point I want to make, that even if de Sitter is realizable, even if the de Sitter conjecture for the Swampland de Sitter conjecture is false, and we could have de Sitter examples, the quintessence models seem to be more natural in string theory, at least as natural in my opinion, and they should be studied. And I think they have not been studied. They haven't been taken very seriously in our community, so I think we should study it. Thank you.
Question?
It's not working. Okay, sorry. I just had a quick question. You showed this plot from z equals 1 to z equals 0. Do you know how far the quintessence field has to roll if you have e to the...
We have checked it. It's less than 1. Much less than 1. Not much less than 1, but we have gone to z of order 1,000 to now. And during the z equals to 1,000 to z equal to 0, it's less than 1. So we have checked those.
Okay, okay.
Yeah, that's a good question. I forgot to mention. Otherwise, that would have been a contradiction.
Yeah.
Part of it, actually, that's related, by the way, to this m Gutt. Because the exponent was much bigger originally. And that's related to that. So it could roll much faster down. So it's a little different. It goes sharper down, in other words. It doesn't roll that way. It rolls steep down. Yeah.
So a question about the value of C. So in the standard model, in the chiral Lagrangian, there's a potential for the pion that has a maximum. So if
those are related to some of the discussions.
Yeah, this last comment you made.
Yes.
Right. So if you don't add anything about V double prime, then there's a claim that constraint tells you C should be less than 10 to the minus 2.
Right.
It's a sharper constraint than
well,
what you get from
the Higgs. Depends on what other additional ingredients you have in those models. You can always put ingredients in those models.
Yeah, I think it's pretty generic though, because it really...
See, that's exactly the point.
Well,
what you're saying when you say generic, you're using generic effective field theory argument, which is fine for effective field theory.
No, it's just that there's a simple argument about the coupling of the quintessence field to the quarks, which is pretty hard to evade.
Well,
You have to couple it to the quarks, otherwise the
there are
constraint is
arguments that people have put forward, and this is one of the papers you are mentioning, I think.
Yeah.
So
Choi and Schmidt.
so there are examples, and people have talked about it. It's too early to decide whether there are covered all possibilities or not. So it's possible that that's the case. Either you get some interesting, strong prediction based on them, or you get the refinement. So the refined version where you're applying it to the metastable one is certainly to be the more conservative version. After all, we're trying to stabilize the universe. We're not trying to unstabilize it. So it's kind of a more natural version anyhow.
Could there be a link between the classical rolling of a quintessence field and the ideas of the inconsistency of the Bunch-Davies vacuum, renormalization of the cosmological constant? Could it be somehow the same?
I think, and this is a good question. I think people, and some people already have, thought about de Sitter in its own right. Forget about how you realize it in string theory or not. Are there quantum inconsistencies with de Sitter? And some people have raised questions like Bunch-Davies, the issue of which kind of vacuum you choose for de Sitter, and whether there are some bizarre features of the quantum aspect of de Sitter. I think that's the way we are going to make progress, to understand whether de Sitter by itself can be as a quantum object makes sense. Now, of course, if it doesn't make sense, we will not be able to realize it in string theory. So that would then connect to this conjecture, perhaps.
You put the example of M-theory, supergravity, and then you say, well, in this case, it seems very hard to get extrema, okay? So, and you argue all the time about the genericity. But I mean, the example you give is like a trivial example, but of course, and it's just a supergravity limit, so we may expect that in the full theory, there'll definitely be more structure. So the fact that you can exclude the Sitter extrema definitely has to come from a quantum gravity property. So have you thought which quantum gravity property is that which forbids the de Sitter extrema?
Well, this is what I referred to here. That is the answer to that question. We should try to understand what quantum aspects of de Sitter are bizarre, regardless of string theory.
Right.
Forget about string theory.
Yeah.
If somebody says, I've constructed de Sitter, what bizarre features there are? People have talked about bizarre features of de Sitter in the past. I mean, people have talked about the instability of de Sitter. For example, Polyakov has talked about different aspects, and there are papers coming out independently of this in the past about, and I don't have anything to add on what people have said. Certainly, I agree that we have to understand quantum mechanically why it doesn't make sense. But I think that the point I was trying to make about the classical is the following. Why do we have to go to non-classical regimes possibly to get de Sitter? Is bizarre. We can get ADS times S, no problem. This beautiful holography, you don't have to do anything exotic. Why do we have to do exotic? Is God malicious? That's the answer. You're saying it might be malicious somehow.
Yeah, I don't know. I would like to understand. Clearly, if there's no solution to an equation, there must be a good reason for that, right?
Yeah, so the question would be that why is it that it's hidden, if at all possible, in bizarre regions? Maybe that's the way it is. Maybe the word was made this way so that theorists argue with each other to see whether we have found it enough fine-tuned or not fine-tuned, distrustable or not. It's possible. But certainly, it's a bit bizarre. That you have to agree.
So you say that. So in your first paper, you've always mentioned that you say that the quantum theory of gravity is the string theory, and from there you make all these conjectures and these statements. Is it possible that string theory has some extra constraints which wouldn't be there in a consistent quantum theory of gravity, or are all these arguments made based on just the quantum gravity effects and not specifically talking about string theory?
Well, I mean, clearly, we do not know any reliable quantum gravity other than what string theory, M theory, etc. gives us. So your question is hypothetical. I mean, I'm going to work on the assumption of the things that we know is based on string theory. If somebody finds evidence that no, string theory is only an isolated island and there's completely different quantum gravity, have nothing to do in any sense in string theory, there should be evidence for it. We haven't seen any evidence of that.
So you talked about how the de Sitter conjecture might follow from the Swampland distance conjecture. I was wondering if that argument would select out regions with unstable directions in particular.
Yes, in the argument that maybe Aaron will mention briefly. So we use the de Sitter entropy. We assume the de Sitter entropy in that argument. But if you have an unstable de Sitter, the de Sitter entropy will not apply. So it's again consistent with metastable, but not the unstable. So that's again consistent with that picture. So the argument slightly prefers the refined version.
Okay, we'll leave it here. We thank Cumrun for his interesting talk.
Thank you.
So the next speaker is Matt Kleban.